So, good afternoon to all. Uh, Greetings from IIRS. Today's lecture is on planetary remote sensing. So, before starting, let me give a brief introduction about planetary geology and remote sensing. Planetary exploration, as we know, is aimed to determine and understand origin of solar system, planets, not necessarily in biological sense, but also in the sense of physical and chemical evolution over time. How did the planets form? To understand the nature of processes that shape our terrestrial environment. Through comparative planetology, we can understand the process on an evolution of solar system object through comparison with other. The nature of planetary surface provides key information about geological, physical, chemical structure of different planetary objects in solar system. Detailed morphological study of planetary surface provide important insights into measures modification processes that are currently active or that have been active at some time in the past. Determination of surface composition provides information on the origin and geological or geochemical evolution. As we can see that these various images of the various geological processes that are active on the planet terrestrial planetary bodies. From impact cratering to surfacial modification processes. So understanding them and comparing it with what the processes that are going on the earth is very important. So let's start with the planetary remote sensing. Now, since planetary bodies tend to be very large, remotely sensed obtained data is important for global understanding of the planet. For geological investigation, as we know, there could be different approaches. Like that on Earth, for understanding, we go to the fields, we bring samples, we do lab analysis, experiments, simulations, and like that. Extraterrestrial planetary bodies simply are too far away for the field samples, so we rely on the samples of the meteoroids, which may be in form of finds and falls and can be used to determine composition and its origin. Also, another approach could be terrestrial analogs that could be defined as an environment, landform, or geological feature or any geological process or activity on the earth that represent one or more aspects of the environment or similar feature or process or activity on that planetary body. So, a terrestrial analog could be a field site which bear an analogy or similarity in some way to other planetary bodies of the solar system. So, these peculiar Earth sites can serve as field facility for or Earth references, as they have particular similarity or characteristic that resemble those found on extraterrestrial planetary bodies. Field sampling, for example, core samples and laboratory measurements are not feasible due to large size of investigated bodies. Also, other approaches as discussed, like and the samples from the meteoroids or maybe like terrestrial analog, are not feasible due to large size of investigated bodies, and they are not sufficient enough, as partially comprehensive samples may only be captured or acquired remotely. So, planetary exploration relies largely or exclusively on remote sensing. So, using remote sensing techniques for collecting these observations from remote sensing techniques may include imaging, high resolution spectroscopy in various ranges of electromagnetic spectrum, or maybe direct sounding or sampling by planetary landers and rovers. Within remote sensing, imaging is of high interest as it allows sampling of large areas at high lateral resolution. A combination of remote sensing techniques from the ground and space led to detailed geological views of many bodies in our solar system. So, it is very important when we study the planetary surfaces. Now, let's talk about the approaches to study planets. So, there can be different approaches in order to explore the planetary bodies to get scientific information. There can be different ways to reach them, either by passing through them through close approach, that we termed as flyby mission. As you can see here, Mariner 2 was NASA's first successfully interplanetary mission, which flew by Venus on December 14, 1962, marking the first time a spacecraft successfully studied another planet up close. Or they can be a different approach, either entering into orbit and start orbiting around it, which we called an orbiter mission. For example, Venera series and the space probe that was deployed by Soviet Union and to gather information about the planet Venus. So they can be orbiter, they can be flyby, or we can reach the surface by landing or roving along. Like just for example, Curiosity rover. So we can land on that planetary surface and bring the or do analysis or scientific studies there. And they can be sample return missions with a goal of collecting and returning samples from extraterrestrial location to Earth for analysis. So there can be different approaches to explore a planet. This is image captured by NASA's Galileo spacecraft in 1992, showing the moon in the orbit around the Earth. It was robotic spacecraft, a space program to study Jupiter and its moon, and was for moon it was a flyby. This is the first image of Earth taken by Mars color camera from MOM mission, Mars orbital mission of ISRO. So now let's explore the topic with focus on remote sensing exploration of Moon and Mars through high resolution optical, topographical, and spectral analysis through various international and Indian mission, and we'll discuss some recent important findings. So today, as we know, till this date, samples of moon rock from Earth's moon have been collected by robotic and crewed mission. So let's first talk about lunar exploration mission. Moon has witnessed around 140 missions till date. Out of them, 53 failed, partial failure were around 5, and 81 were successful. The first direct exploration of Moon started in 1959 during pre-Apollo era. That was era around from 1959 to 1968, where when two space agencies, NASA and Russian space agency, USSR space agency was active, and they launched a series of missions that mainly impactor, flybys, also orbiters, and that some of the name are Luna series, Luna, Zond, Ranger, Surveyor, Lunar Orbiter. So the first mission to surface the moon, starting from successfully hitting the moon surface, was Luna 2. It was a Soviet Union spacecraft. It was followed by Luna 9, that was first successful spacecraft to achieve controlled landing on the moon. And Luna 10 became the first mission to enter the lunar orbit. From then 1968 to 1976, NASA and USSR launched a sample return mission that included manned mission, Apollo programs by NASA, and robotic sample return mission named Luna series, Luna by USSR. Apollo 8 was first successful manned mission that entered into the orbit of the moon in 1968, and it was followed by Apollo 10, then Apollo 11, which became the first successful crewed mission that landed on the moon, then followed by Apollo 12, 14, 15, 16, 17, like that. And Luna sample return mission, Luna 16, 20, 24. Most of these sample return mission, means almost all these sample return mission has sampled the near side of the moon and collected around 400 kgs of samples. Then after a gap of around 15 years, and that has started from around 1990s to present, other space agencies including European space agencies, Japanese space agencies, Chinese space agencies, and Indian space agencies, they has also sent their missions along with the NASA and Russia. So there was missions by these space agencies like European Space Agency Smart 1, Japan's Hitain and Kaguya Selene mission, Chinese Chang'e series, India's Chandrayaan 1, 2, 3 series. And likewise, NASA was also sent like Clementine mission, Lunar Reconnaissance Orbiter, Grail missions. They were there. Now, this is the image of the first image of the moon captured by Luna 3 flyby. It was the first time that we have been able to observe the far side of the moon. Because as we know that the moon is tidally locked with that of Earth, so from Earth we are only able to see the near side of the moon. So for the first time, Luna 3 flyby provided the image of the moon from the far side. And this is the again the far side image of the moon taken by a recent mission, LRO NAC. So this is the means with the time the data resolution has improved, and now the details of the various features could be seen more clearly as compared with the other, the earlier one. Now, these are examples of the samples that has been brought back from the lunar surface, and they are mostly, I will talk about the geology of the moon, where I discuss the moon mainly the surface composition or surface is dominated by volcanic and impact generated material. So this is an example of a basalt from the Mare region, then brick-sheeted material Brixia, and this is the example of an orthosite sample that is representative of the primary crust of the moon. Now, the exploration of the Mars was also divided into different periods. So during 1960s and 70s, Mars was targeted by flyby mission at short distance to conduct experimental measurements. An image of the surface from a close by approach trajectory was taken, and there were examples like Mariner mission. Later, goal targeted on the orbiters and lander and rover missions. So orbiter they started around 1969. A number of orbiters like Mars, Viking, Phobos, Mars Global Surveyor, Mars or Odyssey, Mars Express, Mars Reconnaissance Orbiter, Mars Orbiter Mission, Maven, and ExoMars. These were the orbiters. Many orbiters were sent to the Mars. And then lander and rover mission started in 1962 to 70s. They included Pathfinder, Phoenix, Insight, Sojourner, Spirit of Opportunity, Curiosity, Mars 2020. Mars has a reputation of a difficult space exploration target, and nearly 45% have been fully successful. The challenges, complexity, and length of Mars mission have led to many missions failure. Now let's talk about India's planetary mission, Chandrayaan 1 and Chandrayaan 2. Chandrayaan 1 was India's first mission to the moon that was launched in October 22nd, 2008. That was operational till August 2009. Chandrayaan 1 spacecraft carried a suite of indigenous instruments as well as guest instruments from other space agencies like European Space Agency and NASA. The spacecraft was orbiting around the moon at a height of around 100 kilometers from lunar surface for chemical, mineralogical, and photogeological mapping of the moon. Chandrayaan 1 reached the moon on November 8, 2008. The spacecraft released its moon impact probe on November 14, which crashed as planned as per the mission coordinates into the moon on the same day. The spacecraft operated for 312 days, and it made more than 3,400 orbits around the moon, and mission was concluded when communication with the satellite was lost on August 29, 2009. Data provided by Chandrayaan 1 mission has been extensively used to pursue questions of lunar science and application of remote sensing data, and to understand early history of lunar evolution and assessment of lunar resources. Now, talking about Chandrayaan 2, Chandrayaan 2 was ISRO's second and follow-up mission after the success of Chandrayaan 1 mission. It was launched successfully from Sriharikota on 22nd July 2019. It was a composite module with an orbiter and lander and rover, designed to test capability of soft landing on the moon. Due to hard landing, lander and rover could not be successful, although orbiter was successful and it's still operational. Now, talking about the Mars mission by ISRO. Mars orbiter mission was the first mission to the Mars by ISRO. It was launched on 5th November 2013 and was successfully inserted into Martian orbit on 24 September 2014. The mission was a technology demonstrator. ISRO became fourth space agency to successfully reach Mars, and also made ISRO to reach Mars orbit on its first attempt. MOM has 5 instruments, and it was operational till 2022, and it was orbiting around moon Mars in an elliptical orbit. These are the important payloads of the Mars. Methane sensor for the Mars to measure and map methane in the Martian atmosphere. Martian color camera to monitor the dynamic events and weather of the Mars. Lehman alpha photometer to measure the relative abundance of deuterium to hydrogen in the Mars upper atmosphere. Mars exosphere neutral composition analyzer MENCA, which was a quadruple mass spectrometer, which was capable of analyzing the neutral composition in the range of 1 to 300 atomic mass unit with the unit mass resolution. Then thermal imaging, infrared imaging spectrometer tests to measure a temperature and emissivity in the range of 7 to 13 micrometer region of electromagnetic spectrum. So now coming to the physical parameters about the moon and Mars. Uh, uh, start first talk when we'll talk about the moon. Moon, as we know, is the brightest object in our night sky. It is the fifth largest natural satellite in our solar system and second densest satellite of our solar system. Size-wise, when compared with the Earth, it is about quarter the diameter of the Earth, and it is unique satellite in the solar system, being the largest relative to the planet. The gravitational attraction between Earth-Moon system keeps them in orbit. Rotation and revolution rate of the moon are almost same, and as a result moon does not seem to be spinning but appears to be to the observer from the earth to be keeping almost perfectly still. The image that I have shown in the earlier slide, no, about the far side of the moon, and that this is because of this spinning movement. Moon is from the earth we are able to see only the uh, near side of the moon. The far side is not could not be seen. Now, Earth and Moon form a celestial system with a common center of mass and are considered together as Earth Moon system because of similarity in their formation and evolution. Moon is likely to be formed by a collision between proto-Earth, the Earth when it was formed some 4.5 billion years ago, and it was collided with Mars-sized object, which is often referred as Theia, which occur, as I was told, very closer to the Earth when it was earlier formed, around 4 billion years ago. This impact or collision threw debris into the orbit around the Earth, which coalesced to form the Moon. So moon origin is also related with that of Earth. Moon doesn't have atmosphere, and its axis tilt is negligible. It is around 7 degrees, 7 degree, and density wise, it is 3.34 gram per centimeter cube. Albedo is around 12%, and there is the surface temperature is very rash, ranging from plus 127 degrees centigrade to minus 173 degrees centigrade. So the extreme of temperature is observed on the moon. Now coming to the Mars, Mars is intermediate in size between moon and earth, as you can see here. Mars is the fourth planet from the sun, and it's all outermost of the rocky terrestrial planets that make up the inner solar system. Mars is second smallest planet, as we know. Only Mercury is the smallest. So this little planet Mars orbit around the sun from a distance of about 1.5 times Earth orbital distance. That is at a 1.5 astronomical unit. That comes around 228 million kilometer. So Mars is that distance. The length of one day and night cycle on the Mars is 24 hours, 39 minutes, 35 seconds. However, it is more or less similar to that of Earth. However, its rotational period is around 687 days, which correspond to about 1.8 Earth years. Mars has season because planet's rotation axis is tilted related to its orbital axis, and as we know that an Earth's orbital axis, the rotation axis is also tilted at around 23 and half. So like that, Mars orbital axis is also tilted, and it is currently at around 25 degree. So it also observes seasons. The air temperature of the Mars widely ranges from minus 33 degrees centigrade to minus 83 degrees centigrade at night, and its average temperature is around minus 60 degrees centigrade. So it is a cold planet. Atmosphere wise, Mars has very thin atmosphere, and its composition is around 95% carbon dioxide with rest 3% nitrogen and 1.6% argons and traces of oxygen and water. The atmosphere, this thin atmosphere is very the atmospheric pressure is very less, and it is less than 10 millibar. It is around 6 millibar. which is about 1/100th of the atmospheric pressure on the surface of Earth. So this low atmospheric pressure and temperature, low temperature of the atmosphere prevents liquid water from occurring on the surface of the Mars at present times. Albedo of the Mars is around 15%. It is less than half that of the Earth, and as we know that because Mars presently lacks clouds and ocean that enhance the albedo of the Earth. So this is about the physical parameters of Moon and Mars when compared with the Earth. Now, why do we study Moon and Mars? What is the significance of Moon and Mars study? So first talking about the Moon. Moon is a regular satellite of Earth. Compared to terrestrial planetary body, Moon is unique in terms of bulk density, size, and origin, as we have discussed. Formation of Moon, which occurred much closer to the Earth, 4 billion years ago, and its uniqueness is in terms of its size. As I've told, it is very large related to a planet, and in its aspects of chemistry, may be due to its derivation from the Earth as a result of the giant impact. So, Moon offer unique opportunity to look back into the geological time for which evidences on the Earth has been erased. It serve as a natural laboratory for the planetary process. So, Moon allow the study of fundamental planetary processes like volcanism, impact cratering, and different gravitational environment, essentially in a vacuum. Moon is keystone to understand the processes that shape the terrestrial planets, which have largely been erased, and the geological records has been erased from the first 1,000 million years of Earth history. So it is very important to understand our past. Moon is the only planetary body from which we have samples taken from known location. So remote sensing data can be calibrated and absolute age can be determined using these samples. For Moon, we have data for geology, geochemistry, mineralogy, petrology, chronology, internal structure that can be unequated to any planetary body other than that of Earth. So, by virtue of returned samples from the known geological location, Moon also provide the foundation of crater size frequency distribution chronology for solar system. So these data are fundamental to understanding planetary surface process and geological evolution of the planets and are essential in linking these processes with internal and thermal evolution. Moon has also affected the Earth and evolution of life on Earth in important ways. First of all, Moon, a large body like Moon going around the Earth would stabilize the orbit of the Earth. For example, it's wobbling to provide equitable climate so that extreme temperature do not occur on the Earth. Second, Moon's tidal effect reduced the spin of the Earth from about 5 hours period to 24-hour period. And thirdly, lunar tides brought back marine life from seas where life presumably originated to land, which slowly evolved into land spaces. So, Moon is very important not only to understand solar system history, also to understand Earth, its various processes, and also to affecting its climate and other aspects also. Now coming to the Mars, Mars has similarity as we are told. Mars rotation period is similar to that of Earth. It also observe seasons like that of Earth. And because of presence of atmosphere, there are many geological surface processes and landforms like that of Earth, and the thermal environment is conductive to evolution and development of life. And recent detection of methane, whether its origin is biotic or abiotic, it is very important to understand and know the existence of life on life. So Mars is very important, and also the other aspects of the geology of the Mars and various other aspects like the hemispherical dichotomy. There are various questions to be answered. What are the causes of this hemispherical dichotomy on the Mars? What is the volatile history, origin of the various features on the large shield volcanoes, canyon system, sediment? What is the sedimentary history of the Mars? What is the style of tectonism on the Mars? Nature of the weathered and unweathered material in various areas, at what rates and mechanism, and what are the products of weathering. So Mars is very important to understand all these aspects. Now let's talk about the important geological phenomena that occurs dominantly on Moon and Mars. So, starting with the impact cratering. Impact cratering is a dominant landform on any terrestrial planetary surface and satellites of giant planets in our outer solar system, as well as on asteroids. So, not only in terrestrial planets but also on the asteroids and outer solar means other other than terrestrial planets in outer solar system. It is a very dominant landform. It is the most fundamental geological process in solar system, crucially important for accumulation of planets in the first place, and has played an important role in the formation of most ancient planetary landscape to creation and maintenance of modern regolith of airless bodies. It is a destructive process whereby a projectile impacts the surface of a planetary body with hypervelocity and excavates an orderly sequence, as you can see here. um, in orderly sequence of event that occurs very rapidly in few seconds and eventually produces a circular depression, what we call an impact crater. So it is a principal agent of degradation on airless body like moon, and study of impact crater is very helpful in geological investigation of surface of planets and satellites. So based on the morphology, the impact craters can be classified into different categories. They can be simple crater, complex crater, peak ring crater, and multi-ring craters. Here you can see is complex impact crater from the moon, crater Tycho. It is heavily cratered terrain from the Mars, and this is an example of a crater from the Earth from Wolf Creek, Australia. So let's talk about the various classification of the craters. So a simple crater, as you can see, is a simple bowl-shaped depression with raised rims, and so it is simply a depression with the ejecta material that has been spread radially over it. Now, above a threshold size, which vary with the planetary gravity, the collapse and modification of the transient cavity result in a central topographic peak, which we termed as a central peak, and such craters are termed as complex crater. Here in this crater, you can see a central peak, and around the rims you can see terraced ridges. So this is the peculiarity of a complex crater. Now, when the size of crater, impact crater increases, intermediate size craters, that is from simple to complex, like for example on the moon, it is around 15 kilometer, above 15 kilometer, this be classify mostly they are in the complex crater range, and above 140 kilometer, the peak ring craters. So these in these large craters, where the central peak is replaced by a ring of peaks, which we termed as peak ring craters. And above, even on larger scale, the interior of the crater contains several concentric rims of uplifted material that we termed as a basin. So these largest craters are termed as basins, and they show multiple ring structures, giving appearance of multiple concentric rims. This is an example of a peak ring crater, Schrödinger. It is around 312 kilometer crater present over the south near the south pole of the moon, on the far side of the moon. This transition from complex to peak ring take place at a diameter of around 140 kilometer on the moon and about 20 kilometer on the earth. At even large scale, the interior of the crater contains several concentric rings of uplifted material. Here you can see these largest crater, as I have told, it is termed as basins. And on the lunar surface, there are about 43 large ancient impact basins that excavated and distributed a large amount of material across the entire moon, affecting the geochemistry of the crust. This is the map showing the main topographic rings of the 43 basins of the moon. Now, besides these classification of simple, complex, and based on the sizes, there are some other types of important, unique types of craters also observed on the moon. This is one example of fractured floor crater. These are special types of the craters that are characterized by presence of prominent and visible fracture system on their floor. That's why we term them as fractured craters. They are characterized by anomalously shallow floor, that is cut by radial and concentric or polygonal cracks. And additional interior features are there like moats, ridges, patches of mare materials. And these are examples of fracture floor craters. One is Gassendi, another one is Humboldt from the moon. Then these another class of crater that we termed as PSR, permanently shadowed craters. As you can see, this dark crater. These areas they appear dark. These are present in the polar region of the moon as well as on the Mercury. As we know that the axis of the moon is nearly perpendicular to the direction of sunlight, so the craters present on the polar region, the bottom of these craters are never pointed towards the sun, with some remaining dark over for billions of years. So these craters that are in verge of complete darkness, they are termed as permanently shadowed craters, and they are very important for space exploration and colonization, as they preserve sources of water ices that can be converted into drinkable resource or breathable oxygen or rocket propellant. Now, other than this important dominant land means planetary phenomena, another one is volcanism. So let's talk about the volcanism. Volcanism is also an important phenomena on terrestrial planets and are manifestation of planets' past and present internal heat dynamics. So as on moon, we can see this dark, this is the near side of the moon, and you can see dark patches. They are the means these features are formed by volcanic activity. These are vast magma basaltic plains that has formed by outpouring of the magma on the surface of the moons. And since they have means they have been extruded into the basins of the moons, these circular basins. That's why their shape are more or less circular. So mostly these dark plains, which were termed as mare regions, these are formed by basaltic. They are mostly found on the near side of the moons and tend to fill the bottom of very large and old impact basins. These are high volumes of low viscosity, high temperature basaltic magma that had reshaped the large areas of the moon, and they are covering around 70% of the 17% of the lunar surface, and they are typically around 500 meter to 1500-meter thick and cover nearly one third of the lunar surface, but less than 2% of the lunar far side. These are very flat and smooth mare surfaces that implies that mare lavas were very fluid. Other than these are the dominant volcanic landforms. Other a very small fraction, around 1% of the mare region, is covered by these positive topographic surface features in form of shield volcanoes, domes, and there are also pyroclastic dark mantle deposit, pyroclastic deposits. So these are also manifestation of lunar volcanism. Now these are release regions. These are also means features that has found by volcanic activities. These volcanic features and then are termed as release, sinus release, because there is a river valleys. They are formed by lava flows, by draining of the lava flows, either as a surface channel along which the lava flowed. So instead of these flat plains, they are in form of channels. That's why. So these lava features are termed as release. And this is an example of from TMC, from the sinus relay. And they sometimes the lava drains out, and they can be good candidates for means lava tunnels, lava caves that can be utilized by future explorer humans for shielding them from the harsh environment of the moons. So these are wide scale, large scale lava tubes. So these are example of sinus relay in the valley territory regions. So these are also manifestation of the volcanism on the moon. Now talking about the tectonism, moon doesn't show evidences of plate tectonics. Moon's crust is very thick, rigid, and large major global scale tectonic stresses on the moons therefore are originated not from the convection but from the conduction. These process termed as global contraction is accompanied by tidal forces, impact induced tectonism, basin loading effect, and shallow magmatic intrusion. So lunar magmatic tectonic features are manifested by extensional and compressional features such as faults, grabens, dikes, and wrinkle ridges. This is an examples of wrinkle ridges, which is in compressional features, which are positive relief landforms and broad, steep-sided, and occurs mostly across the lunar mare regions, and are generally regarded as corresponding to fold underlain by shallowly dipping thrust faults. Then these are relays features, which are extensional structures. These are linear topographic lows, fault bounded valleys, and are generally produced by tectonic extension. And relays are narrow channels and are concentric to the rim of the mare or crater floor, and are tension faults created by subsidence of the crater basins. Then there are lobate scrap that represent compressional features that are fault in which side, which is vertically displaced relative to the other side. So these are the various tectonic features of the moon, which are present in form of extensional and compressional features. Now moving on to Mars. So like while moon as we is anhydrous, volatile, depleted, atmosphere-less, differentiated planetary body, Mars is volatile, rich, and oxidized planet with atmosphere, as we have already discussed about the physical parameter of the Mars. So this is a global view of the Mars in equatorial projections. Here you can see the surface of the Mars. This is the image from Mars orbital laser altimeter data, that is topographical data obtained from MGS Mars Global Surveyor missions, that is showing the relief features of the Mars in various colors. The deepest regions, the lowest relief is which is around less than 8 kilometers deep, that is indicated by this violet and blue color, and the highest one is by the white followed by this red color. So here you can see the topography of the Mars, and we can see here in the northern portion it is more or less bluish portion. So this is the low elevation region, whereas in the southern region it is high elevation. So physiographically Mars can be divided into two hemisphere. So there is a hemispheric dichotomy, a low lying northern half that is spacely cratered, and a high southern half that is moderately to heavily cratered, and it has large basins. The boundary between northern and southern physiographic region does not closely coincide with the planetary equator, but ranges up to about 20° north and south. Topographically, it show wide range, height range from around the deepest point at around 7.5 kilometer deep. Deepest point in Hellas Basin impact region in this eastern hemisphere to about 22 kilometer high at the top of Olympus Mons, which is the largest volcano in the solar system. This is Therasis Plateau with the other prominent volcanoes shown here, and these are the canyon system on the Mars. So now talking about the Mars volcanic history. Mars has a rich volcanic history. Volcanism on the Mars shows some dissimilarity with the Earth, mainly due to low gravity and low atmospheric pressure, extensive lava flows. So mostly it is dominated by extensive lava flows. Other than that, there are large shield volcanoes. Large areas are covered by large shield volcanoes, although they are less in number, but they are very prominent. So one example is Olympus Mons. And other than lava flows and shield volcanoes, these are the shield volcanoes also in the Therasis Plateau. This is close-up view. Arcia Mons, Pavones, and Arcus Mons. Then other than the shield volcanoes and lava flows, there are domes type of feature which are termed as tholai. Then there are patera type of features that are considered ancient volcanoes with strong erosion of the flanks. You can see the flanks which are highly eroded. These are impact craters on the Mars, and its surface is covered by various types of impact craters, and like we have classified the impact craters: simple, central peak, peak ring. These types of all impact craters have been observed on the Mars. One peculiar aspect of Mars ejecta crater is unique aspects is the ejecta blanket that surrounds the crater, that are on lobate shaped. and are believed to indicate the presence of liquid water in excavated material. So these types of peculiar ejecta features of the ejecta material of the craters will see on the Mars only, and that indicate the presence of subsurface volatiles. Now, as we have discussed that Mars is having atmosphere, so atmospheric surface processes are prevalent on the Mars, and various erosional and depositional landforms formed by eolene, fluvial and glacial and underground water can be observed on the Mars. So these are example of Mars wasting gullies types of features triggered by liquid water. This is an example of depositional features, a delta. These are sand dunes. These are outflow channels formed by outburst of the fluid material. These are canyon system, that is a long, wide, elongated depression related closely with the volcanism and tectonism. And evidences of water and ice are witnessed in form of pattern ground, in form of polygonal fractures pattern in these soils. So there are wide variety of erosional depositional features that has been observed on the Mars. Now, talking about the tectonism on the Mars, like that of Moon, Mars also doesn't have plate tectonics, and the tectonism on the Mars was also related with the extensional and compressional forces. So we have wrinkled ridges, relief, fault, graben types of features on the Mars that are a manifestation of the extensional and compressional forces, and these are examples of the linear features. As you can see around the volcanoes, these are dike swamps. So both extensional and compressional features are observed on the Mars in form of tectonic activity. Now coming to the Indian missions, Chandrayaan-1 mission, as I have already discussed about the mission that was launched in October 22nd, 2008. It was having an orbiter and an impactor, and it was having 11 payloads. 5 payloads were from India, and other 6 payloads from European Space Agency and NASA. So these are the various payloads that were mainly focused for mapping of the minerals, mapping of the surface composition, topography of the moon, to understand these physical property of the surface and search for water ice, physical radiation environment, magnetic field mapping, chemical mapping, and there was these are the part of orbiter payloads, and there was one impact probe, moon impact probe, that I have discussed. So for mineralogical mapping, there were 3 instruments: HIC from ISRO, high resolution imaging spectrometer, and then SIR2 was from Germany, that is DLR. SIR2, SIR1 was in smart one mission of the European Space Agency. So it is SIR2. It is a non-imaging spectroradiometer. And then M-Cube, moon mineralogy mapper from NASA. It was an imaging spectrometer. So range wise, there were some differences in all these 3 instruments. While HIC and M-Cube were imaging, it was SAR2 was non-imaging. HIC was having 64 bands with spatial resolution of 80 meter, and its spectral range was 420 to 960 nanometer, whereas SAR2 was having 256 band resolutions, spatial resolution of 220 meter, and spectral range of 940 to 2400 nanometer, while M-Cube was having 85 spectral bands, 140 meter spatial resolution, and spectral range from 430 to 3000 nanometer. They were all focused for mineral mapping of the lunar surface. Then for chemical mapping from United Kingdom, it was Chandrayaan-1 X-ray spectrometer. It was a low energy 1 to 10 keV spectrometer for chemical mapping of the lunar surface. Then for topographical mapping, the 2 instrument from ISRO, LLRI, lunar laser imaging instrument, and terrain mapping camera. At that time, terrain mapping camera was the highest resolution camera for the moon. At that time, it was having a spatial resolution of 5 meter, and it was having a stereo capability. For terrain mapping, LLRI used infrared laser pulses to provide altimetry data to accurately map the topography of moon. Then mini synthetic aperture radar operated in microwave region in 2.2 gigahertz to study the surface and near surface features and detection of signature of water ice. Then radiation dose monitor for quantitatively and qualitatively characterizing the radiation environment of near moon surface in terms of particle flux, dose rate, and deposited energy spectrum. Then SARA sub KAV atom and reflecting analyzer from Sweden. Redom was from Bulgaria, Sweden. Sara was from Sweden. And it was mainly designed to image the lunar surface using low energy neutral atoms in the range of 10 keV to 2 keV to map the composition of low energy neutron atom that was kicked off from the outer layer of the moon surface by solar wind. Then ISRO's HEX high energy X-ray spectrometer that operated in low energy X-ray regions for radioactivity mapping for uranium and thorium decay chain nucleotides. So these were the very important instruments on board Chandrayaan 1 payload. Now Chandrayaan 2, and we have discussed about the launch. So we'll go to the payloads of the Chandrayaan 2. Chandrayaan 2 payloads, they were all means modified version of the payloads on the Chandrayaan 1, and they were advanced and miniaturized version of the Chandrayaan 1 payloads. So imaging infrared spectrometer, it was an advanced version of hyperspectral sensors on board Chandrayaan 1, that is HI-C, M-Cube and SIR-2. And then orbital high resolution camera, it is high resolution camera with stereo capability. It operates in panchromatic band with spatial resolution of 25 centimeter, and it is the highest resolution camera at present on the on any orbiter on board moon. And then terrain mapping camera 2, it was a miniaturized version of terrain mapping camera that was used on Chandrayaan 1. Its spatial resolution is 5 meter and provide panchromatic images in stereo triplet with 4 aft and nadir views. Then Chandrayaan, a large area soft X-ray spectrometer class that was designated to measure the X-ray fluorescence spectra. It is continuation of X-ray spectrometer kicks from Chandrayaan 1 to detect X-ray emission in 0.8 to 15 keV range and spatial resolution of 12.5 kilometer. And then solar X-ray monitor, it is companion payload of to support class to observe X-ray emitted by the sun to provide real-time measurement. To provide real-time measurement of solar X-ray spectrum in energy range of 1 to 15 keV and energy resolution of around 180 eV and temporal resolution of 1 second. Then DFSAR, dual frequency synthetic aperture radar with L and S band imaging capability with a swath coverage of 10 kilometer and resolution capability of 2 to 2 meter to 75 meter slant range. The main objective of the payloads are high resolution mapping of the polar region, quantitative emission of water ice in these regions, and estimation of thickness and distribution of lunar regolith. Then Chase 2, Chandra's atmospheric composition explorer. It is sequel of Chase 1 experiment on board Chandrayaan 1. Its main aim is to carry out a detailed and systematic study of tenuous neutral exosphere of the moon from 100 km circular orbit. So now we will discuss about the major findings from the Chandrayaan 1 and recent missions. So first important finding was hydrated lunar surface. So in initial sample analysis of the sample return missions and all these have the result after the analysis indicated that moon is anhydrous, bone dry, and it is mainly dominated by it is refractory minerals and it is volatile free. But the results from the recent missions have changed our understanding about the moon. So let's first talk about the hydration features. So hydration or hydrated indicate OH or H2O. So we can say water or water ice. As we know that water plays a very crucial role in planetary evolution. It greatly influences physical and chemical properties of magmas or thermal properties, and it is a vital resource needed for the human colony, and also plays a fundamental role in planetary evolution. So talking about the moon, as we already said, when compared with the earth, bulk moon is significantly depleted in volatile elements, including the water attributed to violent impact origin of the moon. While small amount of water was reported in the lunar soils returned from each of the Apollo missions, they were generally attributed to terrestrial contaminants. Consequently, in post-Apollo era, the consensus was that Moon was primarily an anhydrous planetary body that contained less than 1 ppb of H2O. So, variety of observations and measurement over past decade has presented new evidences of the water found on the lunar surface environment that has been confirmed by various satellite missions. So they could be different sources of the water. It can be endogenic associated with the magma, or can be exogenic by either by the implant by the cometary or asteroid body, or maybe because of solar wind implantations. So all this type of water has been detected by the recent results from the Chandrayaan 1. This is an example where Chandrayaan 1 M-cube data has using Chandrayaan 1 M-cube data, non-Mare silicic lithology has been examined, and it's detected the water absorption depth, which is at around 2.8 micrometer, and this is due to presence of water OH or H2O that has witnessed the highest water present on the moon. And then besides this endogenic water associated with the silicic lithology, exogenic water has also been detected. This is the global mosaic of the moon generated from the M cube images. Here you can see in the color, various color code RGB, whereas this color indicates, this blue color indicate the IBD at 2.8 micrometer, that is the band absorption depth that was integrated, and in this particular range 2.8 through 3 micrometer range, is to indicate the absorption strength of this particular feature that is present at 2.8 micrometer, and this has been given color blue, and the other 1 micrometer and 2 micrometer absorption has been provided orange and green color. So this indicate that this polar regions is means show high concentration of OH or H2O features, and that indicated hydrated presence of hydrated material. Also, besides this Chandrayaan 1 M cube, the radar data also provided information about the presence of due to means hydrated feature due to presence of water ice in the polar region. This is the polar mosaic generated from the mini SAR data that is working at 2.2 gigahertz, and this is the image generated from for the circular polarization ratio CPR that depends on the electrical dielectric constant of scattering material, and therefore its values can distinguish water and soil and can be used as an indicator of water ice. Here you can see this red color, this points, these are present in the outside of the crater as well as inside of the crater. So here we can see that CPR indicated in these regions, high with high regions indicated with high CPR. So while freshly formed craters show high CPR only in their rough ejecta material consisting of fresh fragments lying outside the crater and not inside the crater floor, which is relatively smooth. So water ice is normally expected to reside within the crater base inside the permanently shadowed crater. In this way, several craters in both north and south polar were identified, and this is how the presence of hydrated feature was observed on the lunar surface through the recent missions. Another important contribution from Chandrayaan 1 mission was discovery of new minerals and lithology from the lunar surface by analysis of its M-cube data that provided spectral variation. And it is a hyperspectral sensors that provided spectra in range of 400 micrometer to around 400 micrometer to 3000 micrometer, no, 3000 nanometer, 400 nanometer to 3000 nanometer. And there, by observing these spectral curvature feature, we can analyze the various minerals. So one important discovery was discovery of magnesium spinel, that is characterized by a broad absorption at around 2000 nanometer, and that was unusual because this particular mineral spinel is supposed to be formed in the it is a metal material, and it was widely distributed on the surface of the moon and discovered by M cube. It was peculiar in the sense because it was not associated with any mafic material. So this was termed as pink spinel and associated with the hyaline material, anorthositic material. So it was pink spinel anorthosite, and it has been globally detected from various tectonic regions, including crater rim, central peak, associated with the silicic lithology, rim of the Mare basins. And not only magnesium spinel, chromium spinel was also discovered from the Chandrayaan 1 M cube. Then Chandrayaan 1 M cube also validated the hypothesis of lunar magma oceans, which says that moon after its formation has undergone global scale melting, and the various this internal stratification of the moon in crust, mantle, and core has been formed as a result of this differentiation process, and that has resulted in generation of a lunar crust, primary crust, which is formed by solidification of the material that has crystallized in the later stages of lunar magma ocean crystallization or fractional crystallization process. So the lunar crust is dominantly composed of anorthosite, or it is a plagioclase feldspar, calcium aluminium silicate, and that is widely distributed on the surface of the moons. So it was known from the samples that moon crust is anorthositic in composition, and also from the data from the early mission like Galileo and Clementine, they has also indicated the presence of anorthosite, but only from the high reflectance. The spectral signature was not available. For the first time, that MQ provided spectral signature of the this anorthosite, and that has been globally mapped, and various regions of the moons which are showing the presence of crystalline plagioclase has been mapped, and that validated the hypothesis of lunar magma ocean. Now, these are some of the results obtained from the other payloads of the Chandrayaan 1, like using the Chase 2, the lunar atmosphere was examined, and it provided the evidences of first important results that lunar atmosphere with an atmospheric pressure of about 6.8 to 10 raised to minus 5 Pascal was at least 2 orders of magnitude denser than expected. Then results from the HEX indicated first attempt to detect emission of low energy gamma rays from planetary surface. Then KICS, that was dedicated for chemical mapping of the surfaces, lunar surface. It has detected various minerals from the lunar surface, and also first time detected the presence of sodium near the crater Tycho in the southern highland region of the moon. Then Sara has observed for the first time a mini magnetosphere above the magnetic anomaly region by means of backscattered energetic neutral atoms. Now talking about the Chandrayaan 2 IIRS instrument and its important findings. So Chandrayaan 2 IIRS I have already discussed as a hyperspectral imager, and that is advanced version of M cube, and the earlier hyperspectral sensor that was flown on Chandrayaan 1. So it specifications like ground sampling, it is spatial resolution of 80 meters, swath of 20 kilometer, and spectral channels are 256, and spectral ranges from 800 nanometer to 5000 nanometer. And this is so it is providing information about reflected as well as thermal emission component also. This is an image of lunar spectral radiance from Chandrayaan 2 data. Here you can see the variation in the reflectance and thermal emission component. These are some initial images of the Chandrayaan 2 hyperspectral data cube. and its comparison with the M cube, because resolution wise it is very high, 80 meter resolution, and spectral resolution is also very high. These are some of the initial results generated from the Chandrayaan for mineral detections. It has detected the presence of various minerals that are present on the moon. I will skip these. One of the important findings from the Chandrayaan 2 IIRS was the clear and unambiguous detection of water, or OH, or hydration feature that we're discussing. So as you can see, water spectra is characterized by absorption at that ranges from 2800 to 3100 nanometer. So you can see the absorption for OH, that is at around 2.8 micrometer or 2800 nanometer, or water, which is around 3000 or 2900 nanometer, and water ice, that is around 3100 nanometer. So these are the various signature of the OH and OH2O and its various phases. So Chandrayaan 1, which is having a spectral range from 500 nanometer to 3000 nanometer, it has observed this absorption depth because of OH or H2O component, but because of the thermal component, thermal issues, it was not able to clearly detect the hydration features. So IIRS, which was having the range beyond 3.3 micrometer or 3000 nanometer, that was up to 5000 nanometer, it has provided a clear and complete characterization of hydration absorption feature from the lunar surface. These are some of the results analyzed where IRS data has been analyzed to understand the absorption, this water absorption feature and its association with lithology, with temperature and latitudinal variation. And these are the IRS data that has been utilized for generating the temperature maps and also analyzing the various surface features and their geology. Now coming to the Chandrayaan 3, Chandrayaan 3 has having payloads for the lander and rover. So Chandrayaan 3 lander payloads, mainly the lander payloads were dedicated for lunar seismic activity, thermophysical experiment to measure the vertical temperature gradient and thermal conductivity of lunar surface. And there was an instrument, Rambha, radio anatomy of moon-bound hypersensitive ionosphere and atmosphere, that was mainly to measure the electron density and temperature near the lunar surface in various solar conditions. And these three payloads were on the lander, and rover was carrying two payloads for elemental composition, surface composition detection. One was LIPS, laser induced breakdown spectroscopy, to analyze. So it uses laser rays emitted by decaying plasma from highly powered laser pulses to understand the or analyze the surface composition of the surface. And another instrument for surface composition was alpha particle X-ray spectrometer, that analyzed the composition based on X-ray emission and fluorescence spectroscopy technique. This is Chandrayaan 3 landing site near the south polar region of the moon, and it was between Manzinus and Bossy-Gold E crater. It is somewhere lying in between Manzinus, the small crater Manzinus Z, Manzinus U, and Bossy-Gold C. These are some of the initial results from the Chandrayaan 3, where the data from the rover and lander payloads have been analyzed, and they have provided some initial results. Like this, LIPS has provided the vertical means the surface composition, emission spectra of the lunar surface, showing the various components. Then CHESTE, which was show variability of the temperature, and this probe for the first time provided the results for temperature variability below the surface and on the surface of the moon in the polar region of the moon. Then ILSA, that measured the recorded the vibration on the landing sites, that may be due to rover navigations. And then Rambha, that has provided initial assessment that plasma encompassing the lunar surface is relatively sparse. And then landing site was also analyzed using Chandrayaan 1, Chandrayaan 2 data, and also to estimate the lunar epiregolith ejection. So how when the lander would have landed on the surface, the epiregolith was ejected, and to how far it has been ejected. So such types of studies has been conducted, and these results has been presented. These are some of the important results from the APXS that has been published in the Nature, and that provided for the first time elemental abundance measure from the southern polar region of the moon. Now coming from the to the future forthcoming mission of the moon of India ISRO for the moon, Chandrayaan 4, that is scheduled in planned in around 2028. It was mainly a sample return missions, and it's carried modules like lander, propulsion module, ascender module, sample transfer module, and Earth re-entry capsule module. It will be focused on the polar region of the moons, and will from where it will collect the samples. Then Chandrayaan 5 LUPIX mission, it is ISRO and JAXA's mission, joint mission, Lunar Polar Exploration Mission. It was planned somewhere near 2029, focused for precise landing near polar permanently shadowed regions of the moons. It has capability of extended survivability. That means beyond one particular day, it has night surviving capability also. It will analyze the volatile, including water, in the PSR regions of the polar region of the moon. So that is all about the moon, Mars, their missions, Indian missions, and their findings. If anybody of you are interested in Indian missions data, you can download. They are freely available from the Pradhan ISSDC sites and ISSDC sites where Chandrayaan 1, Chandrayaan 2, and also MOMS data are available. And there are various tools available there that can help you in means observing from where these data are available, and also for the will help in analysis, and that analysis can be they can be downloaded freely. So that is all about planetary remote sensing, and where I have discussed about the how the remote sensing can help in exploration of the planets, and what understanding we has developed about our near planets, and what are the contributions from Indian missions, and what are the important findings from the Indian missions. Thank you.